Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning, everyone. Welcome to the final day of the summer school. Hopefully it has been a lot of fun. So we have sort of saved the best tutorial for the last. So it's a pleasure to introduce Purushottam. Purushottam is a postdoc at MSR India right now, and before that he did his BTech, PhD and Masters, all three at IIT Kanpur. So over to Purushottam.
So am I audible? Yeah, I think I'm audible. Thanks, Prateek, for that kind introduction. Although I don't have a master's degree, that's something that I miss. I might just go back for a master's degree at some point. Okay, so don't worry about the title. We'll take care of the title later. The slides are available on this website. I'll have it written down so you can check these out later. What we shall actually be looking at in this talk is the analysis of learning algorithms on test data. So in machine learning, we usually take training data that we get, feed it into our favorite learning algorithm and get some model out of it. But what we are really interested in is how well this model performs on test data, that unseen data. And that shall be the focus of this talk. We shall look at how to argue about how well does this learned model generalize to unseen data. Okay? And this discussion shall lead us through some very exciting topics, which we shall go in sequence. But before we do any of that, let's shout out a big thank you to the organizers, without which this wonderful summer school would not have been possible. So the program committee, Aditya, Prateek, Sundar and Manik, the outreach team at MSR, Vidya, Chris and Satish, and of course the technical team led by Vaishak here, who are going to make sure that you and I can watch these talks even after we go back home. So coming back to the agenda, the title was sort of asking a very oft asked question: will it rain tomorrow? In fact, if I remember correctly, we started out this workshop with Satish hoping that the weather would remain cordial for the rest of the summer school. So why are we so unsure about rain? It's not as if we are unsure about the entire physical world around us. So it has something to do with the way we model our weather. We are very bad at modeling weather. So much so that in the current monsoon season, the meteorologist predicted a 15% deficit in the monsoon, whereas what we are experiencing right now is a 45% surplus. We are that bad at predicting monsoon. And the reason for that is we don't understand these systems very well. To make accurate predictions, make confident predictions, we require to have a very deep understanding and precise modeling of the systems involved. And sadly, we are currently incapable of doing that for weather. But there are several other scenarios in which we want to make accurate predictions, but we are unable to because we can't model those systems precisely. And these problems range from medical diagnosis all the way to people trying to sell you stuff online. In all these systems, we have models. So we have disease models here. We have user profiles in online advertising. But these are woefully inaccurate. So we try our best, but we are not able to model these systems exactly, which leads to unsure predictions. And one of the jobs in this discussion would be to analyze how to reason about such unsure predictions. So what better thing to do than to start with the example that we took in the beginning. Let's try to model rain with a very simple and easy to understand model. So let's model rain with the flip of a coin. By that what I mean is, let's say, let's assume for now that rain is decided by some divine entity sitting above, who at the beginning of each day flips a coin. If the coin lands heads, he sends down rain. If it lands tails, no rain. Now, an obvious question now would be, what is the probability with which this coin lands heads? Because that is one of the parameters of the system that we would be interested in. Now, this is a very simple model. Of course, as you can see, this cannot make any predictions. However, this estimate of the bias of this coin will give us a useful statistic nevertheless. What will be the statistic? So, for instance, if I know the bias of the coin for the city of Bangalore on 27th June, then I will be able to say the following, that the probability of it raining in Bangalore on any 27th of June is, let's say, 60%. And that's a useful statistic to know. It does not give me the power to predict whether it will rain tomorrow or not, but it nevertheless gives me a useful statistic. So, but in order to do this estimation, we would need to go into a bit of probability theory. So, we'll gather some tools and techniques and come back to this problem. Okay. Some of this is stuff that all of you have probably been already exposed to, but please go along if you're already familiar with this material. We start off with random variables. Now, the first thing people are usually taught about random variables is that they are not actually variables, they are functions. True, they are not they are technically speaking functions. So, but we'll be more concerned with why do we use random variables anyway. So, in probability and statistics, we are interested in analyzing events. These events may be as simple as the flip of a coin and maybe as complicated as the weather model. However, in all these cases, we have some event space, omega, which consists of lots of events. However, these events are very complex and it's difficult to reason about them mathematically. Random variables give us a way to analyzing these events in a more easy fashion. So, what random variables do is they map events onto the real line. So, instead of talking about a complicated event, you just get to talk about a real number. So, think of random variables as your personal assistants. You are too lazy to, I know I am too lazy to look at this event space and see what's happening. So, my personal assistant does that for me. Whenever an event takes place, he compresses all that information in that event into one single real number. And I just get to worry about that real number. So, given this random variable x, since this is the number this random variable throws up, it is itself random because it depends on a random event, we can talk about things like what's the average value that this random variable takes. So, what's the expectation of a random variable? Notice that I placed absolutely no restrictions on what the random variable does, how it does the mapping. It can do jolly well whatever you wish it to do. And that's the power of random variables. They allow you to be very creative in designing these random variables. So, there can be actually two random variables sitting with you. You have two personal assistants. One tells you the humidity values, one tells you the wind values, let's say, right? So, events take place and both of them give you different values. Given this, one can talk about combinations of random variables. And this single result, which is called linearity of expectation, is perhaps one of the most powerful results, one of the most basic results in probability and statistics, because it allows you to argue about the expectation of combination of random variables, namely the sum. So, the result basically says that the average of two random variables, the average of the sum of two random variables is nothing but the sum of their averages. I would strongly urge you that you try to prove this result yourself. You need only use this definition and the result would pop out for you. Okay. Now, there are other statistics of random variables that are also of great interest, namely the variance of a random variable. So, the expectation of a random variable basically talks about the central value the random variable takes. Okay. Variance talks about how spread out is the random variable. Is it concentrated or does it take widely differing values? Variance is the statistic that captures that information. Okay. One of the most important random variables for us in this lecture and in general would be indicator random variables. Indicator random variables are like alarms that go off when a certain event takes place. Suppose you're interested in a certain event. You can design an indicator variable to signal it off. So, whenever that event happens, the random variable takes a value 1, otherwise it takes a value 0. It's an interesting exercise to look at the expectation and the variance of this random variable, and again I would urge you to do this on your own. These are all available on the website, the URL that I gave you. So, you can go back and do these exercises at your leisure. Interestingly, the expectation of an indicator random variable is nothing but the probability with which the event associated with that indicator random variable takes place. And the variance has some form. Come to that later, but please try to do this on your own. Given all of this discussion about the central value of the random variable and the spread of the random variable, what we are really moving towards is analyzing how random variables are distributed, which brings us to the very rich area of concentration inequalities. Now, concentration inequalities are known by various names. They are called tail inequalities, tail bounds, lots of names in literature, and they come in a huge variety of strengths, specificities, and forms. However, the underlying message in all of these concentration inequalities is the same. Well-behaved random variables always take values about their expectations. So they are actually going to be centered around their central value no matter what, so long as they are well behaved. Okay, you can get all philosophical about this, but what happens is that this behavior of random variables in general allows us to take past behavior of a system and map it onto some intrinsic property of the system, which then allows us to predict future behavior. And that's exactly what machine learning does. Okay. So without further ado, let's move on to looking at concentration inequalities. Before we do that, let's set up things a bit. In the discussion that follows, we shall mostly be looking at not just one random variable, but a sequence of random variables. So we'll have lots of random variables and they'll be identical. So they will be defined over the same event space. They'll take the same values on the same events. It's just that we'll have events being sampled again and again and again, and we'll have the same random variable telling us what is the value of those events that occur. So we'll have random variables x1 through xn, each of them having the same expectation as well as variance. Given these random variables, a very important quantity for us would be the empirical average, which is simply the average observed value of the random variables. So the random variables take some value with certain probability, but if you repeat the experiments again and again and see what is the average value the random variable takes in the observed experiments, that is called the empirical average. Note that the empirical average is itself a random variable, because remember, random variables are just like personal assistants. You have n assistants and you can just have a n plus 1th assistant just looking at the values these n guys give and giving you the average. So this itself is a random variable. Some of the most important properties of this empirical average can be summarized in one line. The expectation of the empirical average is nothing but is the same as the expectation of the individual random variables. Please try to prove this. And the second is that the variance of this empirical average is it looks like sigma square by n, where sigma square is the variance of the individual random variables. Now, this tells us something nice. Independent repetitions of an event do not change its expectation, but bring down the variance. So if you have an event that concentrates around its central value in some way, if you repeat the experiment several times, the empirical average will concentrate around the same central value but much more strongly. So this is the variance reduction phenomenon that we often observe. We'll come to that. That's one of the things we shall prove. That's one of the central goals of concentration inequalities. So it's nice that that question was asked, because that's exactly what we are going to prove now. We're going to prove our first concentration inequality, the famous Markov's inequality. The Markov's inequality holds for any positive valued random variable. So it's a bit restrictive in that sense. So any random variable that always assigns a positive value, what this tells us is that it's very unlikely that that random variable will take very large values, which basically says that it is going to be concentrated around its mean. So as we as we try to see, as we try to make the random variable take values much larger than its expectation, the probability of those events die down. So in terms of pictures, suppose this is the distribution of the random variable, this is the expectation. The probability that the random variable takes a value greater than t dies down as t moves beyond the expected value of the random variable. So basically what we expect. Random variables cannot take very large values as compared to their expectation. Proof. Are you able to see if I bend down? Okay, great. So the proof is actually very simple. First of all, what I will do is simply write the expression for the expected value of a random variable. This is simply the value that it takes on the event times the probability of that event. Now I'm interested in calculating this quantity where the random variable takes a value greater than t. So I should naturally be interested in events on which the random variable takes a value greater than t. So let me do the same. Suppose this is my event space omega. I'll divide it into two parts. Let's say omega 1 and omega 2. Omega 1 will be the set of events on which the random variable takes a small value. Omega 2 will be the set of events on which random variable takes a large value. Okay. Given this decomposition of the event space, what I will simply do is rewrite the expected value of the random variable again. So I'll split that summation over these two sets. Right? Let me call this term A, this term B. Now, what we notice is the following. The summation A consists of terms on which the random variable takes a small value, and on this it takes a large value. So what we can simply do is low bound all of these terms by t, because by definition that is the case. So B is strictly greater than t times summation, right? Sorry for the bad handwriting. If you go to the website, you will find a slightly better written set of annotations. Now, what is this quantity? This is the sum of probabilities of all events on which the random variable takes a large value greater than t. By an application of the union bound, this can be lower bounded by probability that the random variable itself takes a large value. Okay, just try to argue this. This might take a minute, but this is what it is. And if I want to bound A, what I can do is now what's the lower bound on terms in A? A is actually where this consists of events on which the random variable already takes a small value. So what's the lower bound on them? 0, because we assumed, right? Yeah. This one? Not if the events are not disjoint. I didn't make any assumptions about whether the events were disjoint or not. Right? If the events are disjoint, it's an equality. Otherwise, in general, it's an inequality. But union bound holds either way. If you assume that the events are disjoint. Oh, yes. Okay, yeah, right. Sure. Correct. So yeah, this is an equality simply because of the way I wrote the expectation. Right? So now what I have is simply expectation of x being greater than 0 plus t times probability x greater than t, which is actually what we wanted to prove anyway. Okay, nice simple 2 lines of proof, but we should not be deceived by the simplicity of this result. Markov's inequality is the basis behind some of the most strongest some of the strongest concentration inequalities, including Hovding's, Chernoff-Hovding, and Bernstein-style inequalities. And we shall see an application of Markov's inequality right away. Yeah. I have simply decomposed the event space into events where the random variable takes a small value, and on those which it takes a large value.
The left side of expectation, this means the probability is increasing.
What?
Suppose P is to the left side of expectation.
Right. So yeah, you're right. If you look at this, that's a good point. If you look at this expression, it makes a backward statement if t is less than the expected value. So it says the probability of this is, suppose t is half the expected value of the random variable, then this would say the probability x greater than t is less than 2. Probabilities are always greater than 1, so it's a backward statement. This statement makes sense only when t is much, or at least larger than the expected value of the random variable. Oh, sorry. Now notice that this result did not take into account any variance information or any other information about the random variable other than its expectation, and consequently it's a bit weak. A stronger result can be gotten if we take into account variance information of the random variable. So of course, if we have a random variable which has a finite variance, so that means it dies down very quickly, then obviously we expect the random variable to take values that are more concentrated around the mean. So as we go farther and farther away from the mean, the probability that the random variable is going to take values this far is going to die down anyway. So this is that 60, like 30, 60, 90 rule for Gaussians that we have. Okay. And in formal terms, what this inequality, the Chebyshev's inequality, says is that the probability that a random variable will take a value away from its mean in either direction is bounded. It dies down, right? Notice that Chebyshev's does not place any restrictions on what on the sign of the random variable. It can take any values, positive, negative, what have you. Okay. Proof. I'll leave it to you as an exercise. Yeah. Sorry. Oh, yeah. Sorry. Dou p of x is a probability density in case the probability distribution has a density function. Otherwise, if it's a histogram, it's just the probability values. Sorry. P is okay. Yeah, I'm not sure. So I always use square brackets for probability is an operator in that sense, right? It simply works on the probability function. It selects out the density for that. Yeah, I might be making a mistake with respect to established conventions, but please excuse the same. Try this and you will derive Chebyshev's inequality. Okay? Apply Markov's inequality to this new random variable. The next random variable we'll be looking at is a very powerful one. It's called the Chernoff-Hovding's inequality. In its simplest form, it is stated for random variables that take either value 0 or 1. So they're coin flips essentially. So let's take so we have a coin which is tossed n times. Its probability of landing heads is mu at any given toss. Okay. And suppose we toss it n times and we look at the average number of heads that the coin lands on these experiments, then what Chernoff-Hovding tells us is the probability that the average number of heads that it lands being different from its bias is very, very small. So to take an explicit example, suppose we have a coin that lands heads 3/4 of the times. So if we toss the coin 1,000 times, we expect it to land heads around 750 times. Right? So if I come and tell you I tossed that coin 1,000 times and it landed heads 700 times, you'd say, okay, yeah, that's more like it, more or less likely. But if I come and tell you that I tossed that coin and it landed heads 250 times and tails 750 times, you'd say that's very unlikely, right? A loaded coin is more likely to land on the loaded side. It's very unlikely that it tosses it repeatedly and it keeps landing on the unloaded side. Chernoff's inequality captures this very thing, but some aspects of this inequality are notable. Note that the probability that the empirical average is going to deviate from the bias goes exponentially down. It's not 1 by t, it's not 1 by t squared, it's e to the power minus t squared. Another thing, look at the dependence on the number of repetitions. As you make more and more repetitions, as n goes larger and larger, it becomes, this gives you an even tighter inequality. So what it's saying is that if your n is large, it's very, very unlikely you'll get the number of heads to be any different than what is predicted by the bias. You're essentially going to be like locked to the empirical, to the bias of the coin. There is a more general form of this inequality known for bounded random variables. So if your random variables are real valued and take values in some range, these may be positive or negative, then you can get essentially the same result. It's just that the size of the range comes in. Okay. A quick comparison of these inequalities shows us that Chernoff is indeed the most powerful of these inequalities. So if we take the same example, tossing a coin, and suppose we compare what do these inequalities give us in terms of the probability that the average number of heads we land is much larger than compared to the bias, then Markov's actually gives us a result. So again, this is something you should prove. You should prove this at least once. You should see that these are the actual values that come out. But if we try to analyze these bounds, what you find is that in terms of the deviation, Markov's gives you a 1 by t deviation. So the probability that you will be t away is 1 by t. Chebyshev says it's 1 by t squared. Chernoff says it's e to the power minus t squared. Now all of these inequalities are true, which simply means that Markov's is giving you a loose bound. Chebyshev gives you a tighter bound and Chernoff gives you a really tight bound. Also, in terms of the number of repetitions, Markov's is completely silent, and expectedly so, right? Markov's just looks at the expectation of the random variable, and we already saw that the expectation of a random variable, or the expectation of the empirical average, does not change. So it cannot make, so even if you toss this coin 1,000,000 times, Markov's is going to say the same thing. Chebyshev's, because of the variance reduction principle that we saw, gives you a better result, and Chernoff's gives you a really stupendous result. Okay. For instance, if you just want to look at what is the probability that the number of coins will be the proportion of heads will be twice the bias, Markov's gives you a probability half, irrespective of how many coins you toss. Chebyshev's gives you this sort of value 1 by n, and Chernoff's gives you a e to the power minus n style bound. Okay. Given these tools and techniques, we can now quickly go back and try out. Yeah.
Is it because like we have more knowledge about the distribution, we get tighter and tighter?
Exactly. Chernoff is, if you look at the proof of Chernoff's inequality, it does not look at just the, so Markov's inequality uses the expectation, which is the first moment of any random variable. Chebyshev's uses the second moment. Chernoff uses all possibly infinite moments of the random variable. So that's why it's very tight. But it's by no means the tightest inequality. There are tighter inequalities known as Talleyrand style inequalities, which give you even better rates. But then they assume a lot more about the distribution. So as you can see, there's a trade-off between generality and tightness. A result that holds for all distributions will not be as tight, but something that's very specific will be very tight. Coming back, can we estimate so if we want that nice coin that sends down rain, can we estimate the bias of that coin using the tools that we have so far looked at? So suppose we collect rainfall data of whether it rains or not on 27th of June in previous years. Can we use this to estimate the bias of that coin? Yes, we can. Because given our model, we can infer the random coin flips that appeared on those days, and we can use the values of these coin flips to estimate the bias mu. What we have to do is simply set up some random variables, which would be indicator random variables, which take the value 1 if the coin lands heads, 0 if it lands tails. Again, the expectation is, as we have seen, is simply the bias. And what the discussion so far tells us that if we take the average of the coin flicks, the average number of heads the coin has landed in the observations that we have seen, then it will be very close to mu star anyway. So basically what we are saying is, if you have rainfall data for Bangalore for the last 20 years, then you can just take the average number of days it has actually rained on 27th June in the past 20 years and use that as a good estimate of the bias of that coin. Okay, try to work this out yourself. It's nice, it doesn't take long either. However, we can do more. We can, instead of just predicting the probability of rain, we can try predicting the amount of rain as well. So in this case, we model the rain a bit better. So instead of this just a toss of a coin, we have the amount of rain being sent down being chosen randomly from some distribution, let's say. So there's some distribution with some expected value, and suppose there's a bound on this distribution. So suppose it never rains more than 250 millimeters in Bangalore. Let's say someone tells us this, some meteorologist tells us this. Can we now use rainfall data from the past years to figure out the expectation of this distribution? Again, it will be a useful statistic because it will tell us the average amount of rainfall Bangalore gets, let's say in the month of July. By the way, this is actual rainfall data for the city for the past 10 years. And it turns out, yes, if we use a more general form of Chernoff-Hovdings, which looks at bounded random variables, we can, assuming again a bound on the, absolute bound on the amount of rainfall we can get, we can say with 90% confidence, and this calculation again you can do yourself, that the expected amount of rain in Bangalore in the month of July is something like 112 millimeters plus minus 96. Now on one hand, it does give us a useful statistic. It tells us what is the average amount of rainfall in July. It's 111 millimeters. The problematic part is the plus minus 96. It's too much, yes, right? It's way too much. I mean, it's almost as too large to be vacuous. And why is it so? The reason is, again, the modeling is weak. It's a very weak model. Rainfall doesn't get decided by a flip of a coin or some random choice. And in order to actually model rain, we'll have to go to a more complex model. We'll have to, in other words, go to a predictive model of rain. One that can actually predict rain, not just model a bias or a statistic. So what we have to do is model rain as arising from things that we can actually see. We'll have to look at observable quantities and link them to the occurrence of rain or the amount of rain. Once a simple model that I'm giving here is the following. Suppose a meteorologist comes and tells me that the monthly rainfall in Bangalore, let's say in the month of July, depends on the humidity level and wind speed in the previous month, so in the month of June. Now note that we can measure humidity level and wind speeds in month of June, and now we can try to see, does this quantity correlate well with the amount of rainfall we get in July? So again, so we are trying to model the rainfall random variable as a function of the humidity random variable and the wind speed random variable, but there are some unknown model parameters in this model that we are trying to estimate. And we have all this data from the past 10 years to, or whatever number of years, to help us estimate this quantity. Right? So we want to estimate the model parameter for this. Okay. So one simple model that we shall be looking at, and that's actually very widely used in practice as well, is a linear model. So let's say the meteorologist also tells us, and by the way, it's almost okay to model the amount of rain as a linear combination of humidity levels and wind speed. So all we have to find out is what linear combination, because theta 1 and theta 2 are unknown to us. So what we want to do is, using this data, estimate theta 1 and theta 2. In general, building models that link observable quantities to the thing that we want to predict is something that people do all over the place. So in all the areas that we have seen so far, from stock market predictions to medical diagnosis to, again, trying to sell people stuff online, what people do is try to model observable quantities. Like, for instance, in this case, they try to model disease. They have disease models which take into account patient history, scans. In online advertising, companies go a long way, they make huge amounts of effort to model the user in terms of the user's demographics, gender, age, purchase profile, social network. So these are things that one can, yeah, had a question? So these are things that one can observe about any given user. And what now we can try to see is, suppose Purushottam has this user profile and this is his age and whatever, and these are his Facebook friends, and this is how he has been posting on Facebook so far. Can I predict whether Purushottam will buy this laptop or not? So this is what we do all the time, and this is the parametric model of learning. We try to model the quantity of interest, the one we want to predict, as a function of observable quantities and some unknown model parameters. A very popular model in this case is the linear model. Right? So we model the observed factors as well as the linear parameters as vectors, and we try to model the predicted quantity as an inner product between these two vectors. Again, this is something that we have seen even in the optimization lectures that we have had so far in the summer school. We can also look at quadratic models, but we'll mostly look at linear models in this case. Okay, so just a quick note. For sake of simplicity, I'll only look at the regression problems in this talk. So my quantity of interest will always be a real value. We can do classification, but I don't want to get into that complication, right? So even if you want to do classification, you can think of classification as predicting the probability of the point being in a certain class. So if in online tries in Y, I can try to predict what is the probability that Purushottam will buy this laptop. Okay. So the question is, how do we estimate these parameters? How do we estimate these hidden parameters? Usually what we have with us to guide the learning process is a loss or a penalty function. So for instance, if you want to do regression, we have the least squares loss function with us. Okay? And what we obviously want to do is to minimize the error over the entire distribution. So for instance, in the online advertising case, what an e-commerce company would want to do is try to minimize the probability of error it makes in predicting whether all its users will buy a certain laptop. Okay? So in terms of an optimization problem, we'll always model the population risk or the test error, or rather we'll use this notation L of theta for the test error of the model theta. And our end goal in learning is to find out the model with smallest test error. But of course, we don't have access to this distribution, so we can't minimize the test error directly. Just as an e-commerce company cannot ask all its users, oh, will you buy this laptop and will you buy this laptop? You can't ask all your users whether they will buy this laptop or not. It's simply impossible. So what we have to do is work with samples instead. So what an e-commerce company does get are users who actually come and buy their laptops, right? So these are like samples from that distribution. So we have user X1 who comes and probably buys the laptop, and user X2 who doesn't buy the laptop. If you want to convert these buy, not buy labels into probabilities, that's easy to do. What you can simply do is look at the probability of them buying, and look at click-through rates and other indicators to model this. Okay? And what we try to do is, instead of minimizing the test error, we try to minimize the training error, also known as empirical risk. Now recall, this is exactly the stochastic average approximation scheme that Suvrit had talked about in his work, right? Yeah. What does Y? Y is the thing I'm trying to predict. So this might be the probability of a patient having a disease. This may be the probability of it raining tomorrow. This might be the amount of rain that's going to. Yes. So in that case, Y is actually +1 -1. Let's say it's binary valued. Either I buy the laptop or I don't. But usually it's better to model this as a probability. What's the probability of me buying the laptop? Because even if I want to buy a laptop, I might not buy it today. I might buy it tomorrow. So it's usually good to model these as probabilities, even in classification examples. Okay? In general, Y is the thing we are interested in, the one we want to predict. Okay, and so we do empirical risk minimization, and we have seen a huge a variety of algorithms from C.J. Lin's talks, from Suvrit's talks on how to perform this optimization, right? And what we do is we choose the best looking parameter on the trained data. Now, notice I've emphasized the phrase best looking, because what we are not doing is finding the parameter which is actually the best parameter. We are just taking the parameter which looks the best on trained data. So we don't a priori have any knowledge about how this parameter does on test data. So it does well on trained data, that's for sure. However, let's go back a step and see if these parametric models are even that worth the trouble. Do they give us any benefit over, let's say the models, the statistics models that we were looking at? So let's say we try to model rain actually using this data. Let's say perform least squares. You can take this data and fit it into your favorite least squares solver, and you will get something close. This will probably be the least squares estimate of the combination. And it turns out this is a really good predictor. It can really predict rain very well. So in terms of errors, we'll find that in the average error this predictor makes is just plus minus 9 millimeters, whereas earlier we were getting an error of 96 millimeters. What happened? We simply modeled the problem better. We simply modeled the domain better. We simply modeled the system better. We are getting better accuracies. But yet again, there's a caveat here. This error is only on on trained data. We don't know what this will be on test data, and that will be the focus of our talk from now on. Any questions? If not, then this is time to take a short break and watch a video instead. This is a very interesting video because it looks at a problem that's of immense importance in physics, the discovery of the Higgs boson. And we'll see a bit about how did they discover the Higgs boson, and believe it, it will have links to what we are trying to work with as well.
Ever since the accelerator turned on, like a year ago, it's been really totally crazy here. Because everybody comes and sends their students, and it's the center of the world for particles. Things have been running really smoothly. The accelerator is working really well, it's going really fast, we're getting a lot of data. So everybody's really excited. We can discover something any moment. You can hear about some amazing discovery. We're always looking at the data wondering like what's going to pop out of it. Who knows what, right? This is when, last time we talked about surprises, this is when the surprises might happen. So any day could be the day that changed the world.
The LHC is it's really all about discovery and exploration. We're looking for different kinds of things, new crazy kinds of things. I mean, to make up everyday matter, you only need the electron, the up quark, and the down quark. Because with the up quark and the down quark, you can make a proton, or you can make a neutron, right? Electrons and protons and neutrons, you can make any atom. So you only need these three. But there's, how many particles are there we've discovered? 12? Why do we have them? I don't know. How many are there? 100? A million? Only 12? We don't know. We're like looking at the tip of the iceberg here and wondering, is there a huge iceberg under the water, or is this it? And what does it mean in either way, right?
Looking for patterns. It's just like the periodic table.
You take all the elements and you organize them by their characteristics, and they fall into categories. And
these guys over here tend to behave one way, these guys tend to behave another way. Why? Because there's a fundamental underlying structure.
And now we know it's just electron orbitals around nuclei.
So we have a periodic table of the fundamental particles, and like the periodic table, we've been putting it together and trying to organize it by the characteristics of the particles. And it has some interesting features. It has patterns which suggest there must be some sort of underlying structure that we don't understand, that we haven't seen yet. There's 6 quarks.
Up, down, charm, strange, top, bottom.
These guys we call leptons. These are just names.
There's electron, muon, tau.
And
these guys interact with each other. These two interact with each other. These two interact with each other. The same way, these guys are paired. There's all these pairings. Is there more here? We don't know. What's the source of the patterns that we see in this table? We don't know. They're trying to figure out clues by figuring out what other kind of particles also exist. Like what is out there.
the thing is, we have this collider. And the magic of a collider is you can make kinds of matter in a collider that you don't have around. You can take two kinds of particles and annihilate them. And it's not like what comes out has to be a rearrangement of what went in. It's this quantum magic where it sort of disappears into pure energy, and then you can make any sort of particle for which you have enough energy. It's like you have a menu. You go to the restaurant, you have a menu, you're like, I have this much energy, so I can make anything that costs that much energy or less.
So that's why you want to have as much energy as possible. And every time you crank up the energy, you could be exploring a whole new energy range, a whole new regime. It's like landing on a new planet, stock full of new particles nobody has ever seen, because nobody ever had the energy to make them. And as soon as we get over the threshold, boom, they just pop out. And so one of the things people predict is the Higgs boson. The idea is that the Higgs boson is the particle that is responsible for giving mass to the other particles. So you think of things that have mass means it has stuff to it. It's not actually stuff. Earlier I was saying an electron has mass, but has no volume. How can that be? It turns out mass is probably just a characteristic of a particle the way like charge is. Like some particles have charge, like electrons, some particles don't. It's just a different kind of charge. So you can think of mass as sort of gravitational charge. And when two things both have mass, they attract each other. Interestingly, you can't have negative mass or repulsive gravity. So gravity is different from other forces that way. The Higgs theory starts with this. Imagine a field that permeates the entire universe, and every particle feels this field, is affected by this field in different amounts. So some particles are really slowed down by interaction with this field, like swimming through molasses, and other particles hardly feel it. So the ones that hardly feel it, they have a small mass. The ones that are really affected by it, they couple strongly to this field, are slowed down a lot, they have a large mass. So you've turned the question of why do particles have different masses into a different question. Why do particles feel the Higgs field differently? But there is one manifestation of the field is the existence of this particle. So there's lots of different reactions that could give you the Higgs. For example, one is you could have two gluons that fuse, give you a Higgs boson, and the Higgs could decay into two bottom quarks. The problem is, there's lots of other ways to make two bottom quarks. In fact, it's one of the most common things to make. You expect that to happen 1,000,000 times more often from other kinds of processes than from the Higgs. The thing is, we can't see these reactions. We can't like watch them and slow them down, reverse them. All we can do is see the reaction, the decay products from the reaction. So this part is all you see, and what you really want to know is, did this intermediate state exist? Right, so the collision happens, it lasts for like 10 to the negative 23 seconds, and you get one measurement, right? So if you say, well, I'm going to plot the mass, the total energy of this guy. I'm going to add this guy and this guy together and add the total energy. This is this axis here is number of collisions. You do an individual experiment, you get one measurement, right? Here. You do another one, you get another measurement. You do another one. Eventually you build up your data, right? And the data looks like this, for example. And then you have two theories, right, that predict the data. One says, well, I'm going to predict there's no Higgs boson, so the data should fall along this line. And the other is I'm going to predict that plus a Higgs boson. And the problem is the difference between these two theories is very small. And so it's very hard to distinguish these two with our data because the predicted effect is tiny, right? If the predicted effect were huge, it'd be very easy to tell the difference between with Higgs boson or not with Higgs boson. But the predicted effect is tiny, and so it's really hard to see. What you need is a huge amount of data. You need to take a bajillion collisions before you can see the difference. That's why we run this thing 40 million times a second, all day, all year, to get a lot of collisions, to tell small differences between theories. It's like when you take a picture of the sky. If you just take a picture, you get a little bit of light. The longer you leave your telescope looking at the sky, the more you can see farther away things. But there's lots of other things that make the Higgs. There's 10 other ways you can see the Higgs that people are working on that one also. We work in a collaboration of thousands of people, and there's people working on every single channel. Some people are working on this one, some people are working on this one. And the idea is to try to look everywhere simultaneously to see a little bit of evidence here and a little bit of evidence there and a little bit of evidence here can be combined into convincing evidence. So we're going to leave it running for a long time and hope that something new pops out. There's still a possibility for a lot of new things. We've been running for a little while. We haven't seen anything crazy yet, but there could still be crazy pink elephants in there waiting to pop out. That's why I was saying earlier in lunch, like any day somebody could say, oh, we see something exciting. Every time you open your email, like that could be the time you heard about, or every time your student makes a plot. What's in the data? What's in the data? It's exciting.
So what was going on? So it's so funny. The single most common sentence in that video was, "We don't know, we don't know, we don't know." So it really tells us something about our state of knowledge about the world around us, at least the subatomic level. Now, what was happening was these guys were making all these collisions, like trillions of collisions every minute or something, and they were plotting this graph of how many collisions have a certain amount of energy. So they were getting this graph. So lots of collisions have very small energy, and a few have very large energy. However, if there's a Higgs boson present around or being produced, then you get a slight bump in this graph. So it gives a slight boost to the number of collisions at a certain energy level. Now, what was happening was, if you conduct a few experiments, let's say not the gajillions, whatever the word he used, if you don't do those many experiments, you conduct a few experiments, and then you plot this graph based on the experimental data that you do. So you see how many times in your experiments did a certain energy collision happen. Then you might get, okay, this is the contribution of the Higgs boson. You might get a graph something like that looks like this. So in your experiments, what you observed was these energies with this frequency. But if your experiments are not enough, they don't approximate this graph too well, then it's very hard to tell whether there's a bump here or not. So you can't say. However, if you increase the number of experiments that you do many more experiments, then what happens is that you start approximating this graph uniformly well. So your reconstruction of the graph is very close, so that now the bump is very clear, and you get a Nobel Prize for that. But what happened here was, in the earlier case, what was happening was the variations in the other energy levels was so large that it was swamping out this bump. This bump is a tiny bump, as that guy was saying. So in order to figure out whether the bump is there or not, you need to bring down the variance at the other portions of the curve down, so that the bump can be made apparent if one is there to begin with. Something very similar happens in learning, surprisingly. And we shall look at it in the next section. So just a quick recap. What we do is take training samples, sample from some distribution, and choose the best looking model, whereas what we really want is the best model in terms of test data. So and we are now faced with the question, is the model that has the best training error also the best model on test error, or is it close to the best model on test error? Can we say something about that? Now notice that we have already had a discussion on Chernoff bounds, which say that empirical averages do converge to true averages. Now you might be tempted to say, why don't we apply Chernoff's bound to this theta hat, the parameter, the model that we learned using trained data? But remember, for Chernoff-Hovding bounds, the observations need to be independent. So if you have, let's say, some fixed model in mind, and you evaluate that fixed model on training data, then the performance that model has on training data will be roughly close to its test performance simply by an application of Chernoff's bound. But since we fitted this model theta hat to the training data, these training samples are no longer IID for this. They have become correlated. So we can't apply Chernoff bound, because remember, in principle, we could have overfit to the data while learning this model. So there is no a priori guarantee that the test error of theta hat is going to be small as well. However, what we are going to do is exactly the following. When is it, we are going to argue, when is it that the model that looks good on training data also is a good model on test data? Now it turns out that a sufficient condition for that is that no one should fool us on trained data. No model should be deceptive. So we have all these models clamoring to be chosen because of their performance on test data, and we pick one of them. We would have picked a good model if no model is going to give a deceptive performance on this trained data. By that what I mean is, no bad model should appear good on training data. So if a model has bad performance on test data, it should have bad performance on trained data so that we don't select it. Similarly, no good model should appear bad on trained data. If there's a model which has very small error on test data, it should have small error on trained data as well, so that we do select it. Turns out, if these two conditions are satisfied, which means that for all models in our model class, if the training error and test error are close, then what we can argue is that the test error of our learned model will also be small. Okay? This is what I actually wanted to prove, that the learned model is actually good. The proof is literally 2 lines of arithmetic. So what? Oh, sorry. Yeah. So we from now on we'll call this phenomenon to be uniform convergence. So we'll assume that the training error converges to the test error for all models at the same time in the model class. That's why the term uniform convergence instead of pointwise convergence. Okay. So suppose we have uniform convergence, then what we are interested in is the test error of the learned model. Because of uniform convergence, we know that the test error of the learned model is not large compared to the training error, right? This simply, I'm sorry. So this is simply rewriting, this is simply by uniform convergence. The test error of theta hat is nothing but the training error of theta hat plus some epsilon. Now, theta hat was the model that achieved the best training error. So its training error has to be less than the training error of the best model for test data, the theta star. And we apply uniform convergence again to get that this quantity that we have is less than this, right? And we are done. This is what we wanted to prove. The training, the test error of the learned model is not going to be very large compared to the best test error possible. Any questions? Okay. So it seems that this quantity is of immense importance to us. If we are able to bound this quantity, we are able to bound the generalization error of our learned model. We shall call this quantity the uniform deviation for this class. So if the uniform deviation for a certain model class goes to 0, it means that the model that we have learned from that class is a good model on test data as well, right? In the following, what we shall show is that as the number of training points goes to infinity, the uniform deviation for the model class that we shall look at does indeed go to 0, which basically stated differently means that a large enough randomly chosen training set is not going to discriminate or favor any model. It's going to be fair to all models, roughly fair. So whatever is their training error is going to be close to their test error as well. An interpretation of the same principle closer home is in exams. So suppose we have hundreds of thousands of candidates which we want to consider for, let's say, a few seats, let's say one of these entrance examinations. Ideally, we would have liked to interview all these candidates individually, but we can't do that. It's simply too much time. It takes simply too much time. So what we do is we make them take an exam and we give them the same question paper. So what this principle is saying is that if we have an exam with enough questions and enough variety of questions, then no ill-prepared candidate will pass, as well as no truly good candidate will get rejected. Okay? So if we just use the exam results to select candidates, we will end up selecting a good candidate. Okay? So let's start by, so the only thing that we have left is to prove the uniform deviation bounds for certain model class. Suppose we start with a very trivial model class. This model class has only one model. So there's just theta 1, and as you can imagine, theta 1 is theta star. So we want to prove the uniform deviation bound for this model class. How can we do it? So we simply have to show that for theta 1, the test error converges, or rather the training error converges to the test error as the number of samples grows to infinity. And that is actually, as you can imagine, just an application of Chernoff-Hovding's bound. To apply that bound, what we simply do is we construct a random variable which takes a data point, so the feature vector as well as the true predicted value, to the loss that this model has on that data point. Right? So let's say we are doing regression, so it's just measuring how far is y from the predicted value by this of this model theta 1. Okay, so if we have data points x, if we have n data points, then correspondingly we'll have n random variables here. Okay, these are empirical observations of this random variable. Now all we need to do is observe that the empirical average, which is simply the average of the observed random variables, is nothing but the empirical error or the training error of theta 1. Okay, that's simply by definition. Also, what we know is the expected value of this random variable when xy is taken with the entire domain, the entire population, is simply the test error of this model. Or, sorry, z hat as in? Expected value of z. So z is a random variable derived out of x and y. So yeah, this expression of over a different random variable. So now we can apply Chernoff-Hovding's bound. There's a small technicality here. Chernoff-Hovding's bound requires the random variables to be bounded. So simply assume for now that the loss function is bounded. So it's always less than b. So it's positive and always less than some quantity b. So this holds true for logistic regression, least squares, what have you. And if you apply Chernoff-Hovding's bound, you will get that the uniform deviation for this model class goes down with n. So as the number of samples goes to infinity, you do converge. Okay. So far so good? Because this is something that we shall now bootstrap upon to get more complex results. So suppose we have a model class that has not just a single element but a finite number of models. So one of them is theta star, we don't know which, and now we are trying to bound the uniform deviation for this model class. So the maximum deviation any training error has from any test error for the models in this class. Suppose you want to bound this. How do we do that? Remember, in the earlier in the analysis that we just did, we showed that for any fixed model in this class, the probability that its training error will be very far away from its test error is small. So let's say that probability is delta n. Okay, we are shooting to show that we are shooting for the result that E of theta is less than epsilon. So it makes sense to talk about this quantity, right? So the probability that the deviation for any single guy is greater than epsilon. But this is not what we are interested in. We are interested in is the uniform bound for this deviation. What we need to do is simply, at least in this case, apply the union bound or the Boole's inequality as it is called to get that uniform bound. So this is what we are interested in, right? We are interested in the probability that any of the models does not converge, as in their training error doesn't converge to their test error. That's other way of saying is that what is the probability that max of the deviations is greater than epsilon. Another way of writing is that the probability that the union of these events happens. What are the events? That we have h events here, so correspond to each correspond to one element in the model class. So what is the probability that any one of these guys is going to not converge or have a deviation that's greater than epsilon? Now you apply union bound. The probability of a union of a set of events, irrespective of what they look like, is bounded by the sum of the probabilities. Simply bound this. Now we are in familiar domain. We have already bounded each of these guys individually. So we just plug that in and get this result. So notice that this is identical to the earlier result, but the number of models in this class is coming here as a log factor. So it's still not very bad. So your n needs to be at least greater than log h. So if there are h models in your class, you need at least log h training samples to figure out a good model in that class. Okay. Any questions? Good. Let's make things more interesting. Infinite hypothesis classes. The previous analysis fails miserably because even though h appears as a log of an infinite, or rather the divergent quantity is divergent, so we cannot use the earlier bounds anyway. So in fact these are the model classes that are used in practice. So in many regularized learning frameworks such as SVMs, what we are really interested in are models in d dimensions, let's say whose length is, or d-dimensional vectors whose length, Euclidean length is less than r for some r, right? So this is an infinite model class. Now we want to argue that uniform deviation is going to be small for this model class as well. How do you show that? Can't count the number of models in this class explicitly because there's an infinite number of them. So what we need to do is count them a bit more carefully. And these so-called capacity measures are exactly that. They are more clever ways of counting how many models are there in hypothesis class. And there's a huge number of them for different applications. For sake of simplicity, we'll be looking at just one, covering numbers, in this talk. So let's get down to this argument. So we shall show that even though this class is infinite, its effective size is not infinite, it's finite. To go through the covering number argument, we need the notion of a Lipschitz function. A Lipschitz function is nothing but a function that doesn't jump too much. So picture the step function. Takes value 0 on negative values, takes value 1 on positive values, right? That sort of a function is, so this function, let's say, this function jumps abruptly. This is not a Lipschitz function. Lipschitz functions change gradually. So for now, if you want to think about in a slightly simple manner, think about Lipschitz functions as functions that are smooth and differentiable. They need not be differentiable, but for now, let's take them to be so. Examples, least squares. Least squares functions, this least square loss function is Lipschitz because if I change my prediction a bit too much, so if I move a bit away from the true value, the loss I incur does not jump abruptly. It does increase, but it increases in a smooth manner. In classification, we use the logistic loss function, and again, if I change my prediction a bit, the loss that I incur on that prediction does not change too much. Okay, so this is what it's saying. If I change my prediction too much, the loss does not change too much. Okay. Now, what we shall prove now is the following: that if we are working with the Lipschitz loss function, and suppose I want to talk about the uniform deviation of a certain model class, then one of the things I want to do is get an effective count of the model class. So I cannot count all models. So what I will say now is the following. If I have a Lipschitz function, and I'm, let's say, working with linear models, then I don't need to count models that are similar to each other twice. So if we have two models in the model class which are very similar to each other, so let's say they are vectors and the vectors are very close to each other, then when I'm counting the effective number of models, I don't need to count these twice. Why? Because what I will show is that they will have the same training error or very similar training error as well as very similar test error. So the claim we are making is the following. The formal claim we are making is the following: for an L-Lipschitz loss function and linear models, for any training set we have the following result. If two models are close together, then their training errors are going to be close as well. Now notice this is not a high probability statement. This is a deterministic statement. For any training set, this holds true. That means these two models are bound together. They are bound together for life. They will never give different performance on any training set. as well as they will not give any different performance on test sets, on the test error as well. So if two models are close to each other, they will have very close training error as well as very close test error.
We can always find such L to satisfy this.
Yes, but if that L diverges, then it's useless, right? What about the classification error? Sorry, this step function. This is the misclassification loss, looks like this, right? If you change, if the correct label is +1 and you are predicting plus 0.0005, then you get a loss of 0 because you are predicting the correct sign. However, if you change slightly to the negative side, your loss suddenly shoots up to 1. Right? So in that case, I can make L arbitrarily large. In fact, it's divergent. So there's no finite L for which this is satisfied, and consequently, the learning theoretic guarantees don't go. And there's a reason. This is not just mathematical, impreciseness or something that we are lacking in our analysis that is preventing us from getting these discussions, getting these things through. Minimizing, what I will show you is that I can actually minimize test error for the Lipschitz loss functions that we are considering. Minimizing misclassification loss is actually NP hard. So there's something much deeper about it. It's not as though our inability to argue things a certain way is preventing us from making these statements. Okay?
How can we have two hypotheses for one training set? We should have different training sets.
No, I'm not saying there are two hypotheses for a training set. I'm saying that I have two hypotheses that are very close together. They will have similar errors on any training set. These are not the hypotheses that I'm learning using the training set. No, these are not theta hat n. These are two. There's some two hypotheses that I've considered, which are close to each other. All I'm saying is that if they are close, they will have the same training error. You should expect this, right? Suppose you're doing linear regression. And suppose you're working with a certain model vector. If I add 0.00001 to each of the coordinates, I mean, this should not make a big difference to the predictions. And since these are Lipschitz loss functions, if the predictions are not very different, the errors are not going to, the loss is not going to be different as well, right? However, it can be very different if the loss is non-Lipschitz, because there I can adversely change slightly the prediction and suddenly make the loss very different from what it was. Doesn't happen for Lipschitz loss functions. Okay. The proof I'm going to skip because I'm running short of time. It's a very simple proof, just uses Cauchy-Schwarz inequality at one point. So this proof is given in the slides on the website. We can just go through it. It's very simple, not a big deal. What I really want to do is use that trick, or rather use that result to explain the covering number argument. So what we have shown so far is the following. If there are two models in our model class that are very close together, then the training error is close as well as the test error is close. And the training error is close on any training set. Now I'll use that statement, these two statements, to prove that if I have two models that are close and one of the models has converged, which means the training error in that model is close to its test error, then it is also true for the other model, right? So the moment a model converges, all models around it converge as well. So in particular, if there's any model which is close to it, the moment the central guy converges, it makes the other guy converge as well, deterministically. How do you prove it? It's actually not that hard. Sorry. Let me call this thing L hat 2, this guy L2, this guy L hat 1, and this guy L1. So why I have four quantities with me, L hat 1, L1, L hat 2, and L2. Since these models are close together, theta 1, theta 2 are close together, I know that these are epsilon away as well as these are epsilon away. Let's say they are not epsilon but L into epsilon away, right? That's simply because these models are close together and the previous result. And now I have assumed that theta 1 has converged so that these two guys are close together as well. All you need to do is now apply triangle inequality to show that follow this path and you will see that L2 hat is also close to L2. So the moment L1 converges, L2 converges as well. In other words, the moment a model converges inside the model class, it forces every model to converge in its vicinity. That is a powerful statement, because what we have done is in one shot made an infinite number of models converge. Remember, this ball around theta 1 has infinite models, or may have infinite models, and we don't care. All of them converge simply because the central guy has converged. We can now use this trick to bound the uniform deviation for an infinite model class. What we simply need to do is, and that's why this actually is called a covering argument, we simply need to cover this model class using balls centered at some models. Okay, it's important to note that these models are not chosen based on training data. This just depends on the model class. If we are looking at a model class, we can a priori, even before looking at training data, fix these centers and draw balls around them so that the balls cover the entire model class. Now, if someone comes and tells me, and these balls are all of radius epsilon, right? Okay. So if I'm able to cover this model class with balls of radius epsilon, and someone comes and tells me that I'm able to ensure convergence on the center of these balls, so there are 8 balls here, 8 balls are sufficient to cover this set. If I'm able to ensure that convergence is taking place in the centers of these 8 balls, then the previous result shows me that all these balls converge, but the balls together cover the entire model class. That means the entire model class converges, which means the uniform deviation is bounded the way we want. So we have, as you can see, effectively reduced the size of this model class from infinite to finite. Okay, these are only finitely many. Okay, so I should not say they are finitely. For many interesting model classes, the covering number will be finite. Okay. Now the only problem left is to ensure the convergence of the empirical risk to the population risk, or the training error to the test error, on these 8 models. But that's something we have already done, right? This is simply the h in the earlier. Okay, so we can, if we take n to be greater than, let's say, log h by epsilon square, then we are usually good to go. So all these 8 models will converge. In this case, h is equal to 8. All these 8 models will converge, and they will make every other model in this model class converge. Okay, and as you can imagine, there is a yeah. That's the beauty of this, right? We are trying. We are. Oh no. Wait. The convergence of these 8 guys will be based on training data. So they happen with certain probability. They are not sure. All these 8 guys are not. They are not guaranteed to converge, but they will converge with very high probability. However, the result that is training data independent is that if these 8 guys converge, then the entire model class converges. Okay. The minimum number of such balls required to cover a model class is known as the covering number of that model class. So of course, it's a parameterized quantity. So the minimum number of balls required of size epsilon required to cover a model class is known as the epsilon level covering number, or the covering number at scale epsilon for that model class. And for a large number of interesting model classes, this covering number is actually finite, in fact very small. And you can try to thrash out the details to see that if the covering number of a certain class is bounded, then the uniform deviation can be bounded in this case, in this way. Yeah.
How is this value epsilon decided?
This can be whatever you want.
Is it something related to, like, since the epsilon value controls the number of balls and the covering number? Is it?
Okay, so yeah. Yes, so as you can, that's a good question actually. As you can imagine, if your epsilon is very small, if you're using very small balls, you'll need larger number of balls, right? So a larger number of balls means the h grows large, which means n has to grow as well, which is basically saying that if you want more accurate predictions, if you want, so remember at the end of the day, the result we have is the following: L of theta hat is less than L of theta star plus 2 epsilon. If you want that epsilon to be small, you will require smaller balls to cover the hypothesis class, and you will require more number of training points.
That like selecting epsilon would also be like some model selection?
No.
By bias values?
The epsilon is usually determined once you have a certain number of data points. So the result is of the following kind: if you want an epsilon accurate solution, which means that L of theta hat is less than L of theta star plus epsilon, let's call that an epsilon accurate solution. If you want an epsilon accurate solution, you need n to be greater than 1 by epsilon squared. So n and epsilon square, n and epsilon are linked to each other. The moment you fix an n, you get an epsilon, and the other way around. We'll see one such example. Now, bias variance trade-off. This is something that appeared in John's talk. He talked about bias variance trade-off a bit. What is a bias variance trade-off? Let's see formally what does a bias variance trade-off mean. So in the earlier example, what we saw is that the uniform deviation is bounded by this quantity, right? The probability that the uniform deviation is greater than epsilon is less than this thing. Depends on the covering number. Now you can take one step. You can use the earlier result to show that if the uniform deviation bound is of this kind, then the excess risk or the generalization error can be expressed in this form. The probability that with very high probability your learned predictor will have a small test error as well. Now this is actually what sets up a bias variance trade-off. Now notice, if you have a very large model class, you have a very powerful model class, then what will happen is that L of theta star will typically be small, because you'll have very complex models sitting in the model class. So the best model in that model class will be able to achieve very small test error. So L of theta star is going to be small. So you might get excited. Oh, I can bring down L of theta hat to be very small because L of theta star is very small. But there's a caveat. If you have a large model class, then you have larger variance as well, which is exactly what we were talking about. If you have a large model class, its covering number is large, okay, which means larger variance. On the other hand, if you have a very small model class, in the limit you have just one model in the model class, you will have larger error because there's just one model to choose from. If it sucks, it sucks. You can't do anything about it. You can't optimize at all. But you'll have very small variance because the covering number of that model class is going to be small. This is exactly what is known as the bias variance trade-off. The size of the model class, how to decide the size of a model class, is a central problem in machine learning. And many things that you see in literature like regularization, cross-validation, structural risk minimization are nothing but trying to address this bias variance trade-off. All of them are trying to restrict the model class size to be such that it's not too small and not too large. Okay? This was just a footnote to link things to what we have seen previously in the summer school. So in the last 5 minutes, let me try to attempt to give you an example of why covering numbers of infinite model classes can be bounded. I'll look at two interesting classes which have appeared frequently in the summer school lectures. One is the bounded norm model classes. So if you're looking at SVMs or logistic regression, you're looking at linear models where the model is a d-dimensional vector with a finite radius, let's say r. Turns out that the epsilon covering number of this model class can be bounded something like this. It's like r by epsilon to the power d, it's exponential in d. What's the proof? Let me sketch the proof. The complete proof is present in the slides on the website. This is the model class pictorially. It's a ball of radius r in d dimensions. Turns out, in order to bound the epsilon covering number, I'll need what are known as epsilon well separated sets. So let me place points on in this ball that are epsilon separated. So each one of these points is far away from each other. Each of these points is at least epsilon away from each other. So this point is epsilon away from every other point, and so is this, and so is this. Let me choose a maximal set of this kind. What do I mean by that? I want to choose a set of points that each point is epsilon away from every other point, but I cannot add any more points to this set without violating this separation. This is known as a maximal epsilon set. What you can argue, go back and argue, is that a maximal epsilon separated set is always an epsilon cover, because of the same reason, right? If I can't add any more points to this set without violating the separation principle, that means for all points in this ball, there must be an orange point that is epsilon close, right? Simply by contradiction. So now what I do is I place balls of radius epsilon by 2 at each of these orange points, and these balls are disjoint clearly because these points are epsilon separated. Note that all these balls lie in a larger sphere of radius r plus epsilon by 2, right? And now what we can simply do is use volume arguments in higher dimensions to get this result. Please check the website for details. Okay. However, what is interesting for us is the following, that if we are working with a small class, then the uniform deviation is bounded in this way. More importantly, if I take enough number of samples, so if my number of samples is greater than something like d by epsilon square times log 1 by epsilon, then my generalization error for theta hat will be less than epsilon. Okay, I'm missing some constants here, but those are fine. The important thing to note here is that the number of samples required is d by epsilon square, ignoring log factors. This is important because of the second thing I'm going to look at, sparse models. So remember, in Pratik's talk, we were looking at models that are high dimensional but are sparse. And one of the central things in the central themes of the talk was the advantage that we get out of working with these sparse models, because as Pratik mentioned, they take less training data to train. Do they really take less training data to train? Let's see. It turns out that one can bound, again please look at the website for the proof, one can bound their covering number, the covering number of the class of the bounded sparse model class, in this manner. And it turns out that to get an epsilon excess risk, epsilon generalization error, you now only need s log d by epsilon square. Remember, this is exactly what was mentioned in the sparse recovery lecture, that if you're working with s sparse models in d dimensions, the amount of trained data you require is just s log d by epsilon square. Okay? So this in some sense is theoretical proof that yes, working with sparse models is indeed beneficial when you're working in really high dimensions as well as don't have enough training data. So to summarize, and this I'll just finish in a couple of slides, what we're interested in and what we do in practice in machine learning is empirical risk minimization and training data. However, we are unsure about whether the model we choose using ARM is actually good on test data. We saw that uniform convergence in the form of bounding the uniform deviation of a model class is one way of arguing for the test error of the learned model. To do that, we looked at Lipschitz loss functions and a covering number argument to bound the uniform convergence, the uniform deviation of model class. For several interesting model classes, we were able to show that using a volume argument, the covering number of these classes is indeed finite, and using all these steps, we are finally able to get the kind of result we want. So if your number of trained data points is more than 1 by epsilon square times some things, ignoring constant factors, then with probability at least 1 minus delta, the test error of your learned model will be no more than the best test error possible plus epsilon. Okay, so this is the goal that we have started out with. We have completed that goal in some sense. Some remarks. There are tighter bounds possible. ones that get rid of D for certain model classes, ones that get rid of this log factor for certain model classes, ones that make this, instead of 1 by epsilon square, require only 1 by epsilon training points. Those are more advanced results, but require us to rework the entire analysis and have counterparts to all these steps that we took. Okay. These are some very nicely written monographs as well as books which detail some of the arguments that we have looked at today. Encouraged to go back. In particular, this monograph is especially well written, and these are actually in order of advanced material. So you should start with this, maybe go to this, and this book is, I mean, if you're really sadistic about, you know, looking at very complex and tight analysis, you should look at this book. A beauty of a manuscript, but very advanced as well. Okay, so I'll stop here. If there are any questions, I'll take them.
All right, so thanks to Purushottam, and let's have a
Nice, thank you.